Okay, welcome back to part 2 of the lesson on critical points and critical values. We just completed example number 2 on page 10. Don't forget we used a table to determine if critical points represented maximum or minimum values. That method is sometimes it's called the first derivative test, or sometimes it's just called using a table to determine maximum and minimum values. But if the question asks you to determine where is the graph increasing or on what intervals is it increasing, that table is absolutely necessary. If you look at example number 3, find those values of x for which the function, and here's your function right there, all right, that's another cubic, is increasing, and those values for which it is decreasing. We are definitely going to require a table like we did for example number 2, and then identify any points as maximums or minimums. So this time you're going to require the y values as well. So let's go ahead and remember now what we do to identify the critical values is the first thing we do is we calculate the derivative of that function. Actually, there's only 2 terms in it. It's only a binomial. So you're going to add 3x squared, and then negative 3x squared is going to become minus 6x. So there's your derivative. And now we'll set that equal to 0. So 3x squared minus 6x is equal to 0. Actually, this one looks familiar. I think this is the same one as on the first page. So we have a common factor of 3x in front of this. It certainly is the same as the one on the first page. In front of x minus 2 equals 0. And of course, now you have the 2 pieces. So if 3x is equal to 0, that tells you that x is equal to 0. And if x minus 2 is equal to 0, well, that tells you that x is equal to 2. So there's your 2 critical values, the x values only. And now if you wanted to, you could at this point even plug those back into the original function. It's not that difficult of a calculation to do. So for example, if x is equal to 0, you might as well get y's here now because you're going to need them. So the y value, if you plug 0 back into the original function, remember, you get back another 0. So 0, 0. Well, that's the same thing that we got back on the first page, remember. And if you plug in a 2, back there on the first page, we got y is equal to negative 4. Okay? So the 2 points are, one of them is 0, 0. Now it's either a max or a min. And the other one is 2, negative 4. And so that one is either a max or a min. But there's your critical points right there. So what we do now is we make a table. And remember, if you have 2 critical values, you're going to need a table with 5 columns. If you had 3 critical values, you'd need a table with 7 columns. Remember that for example 4. So here's what we do. We're going to make our table. I'll make it big right here, say. Okay, and 1, 2, 3, 4, 5. So these are your x's right here. And you put the smaller x value into column 2. Well, let me see, 0 and 2. So I'm going to put my 0 there. And I'm going to put my 2 in column number 4 now. So there's my x values. All right, there's my x values. And remember, for the second row, you're actually going to determine what the derivative is at that point. Is it positive or is it negative? But you know that at the critical values themselves, the derivative is 0 because they're maximums or minimums. And the graph is actually flat, kind of like that. You can just draw a couple of horizontal line segments. Now, here's where the imaginative part comes in. You've got to pick some numbers that fit in between those critical values. Like you need something smaller than 0. You need something bigger than 2. And you need something in between 0 and 2. Well, I'm kind of thinking there's some pretty obvious numbers there for that. So something a little bit smaller than 0. Like I just picked like negative 1. Don't pick a weird number like negative 3.77148. It would work, but just make the numbers easy. Something between 0 and 2. Let's pick something like a 1. And something a little bigger than 2. Let's pick a 3. So what you do now, one at a time, is you plug those x values, the ones that are in between or on the extremes of your critical values, into your first derivative. So if you take your first derivative, now remember, there's your first derivative right there. If you were to plug in negative 1, you would get back, if I'm not mistaken, you would get back a value of 9. Okay, so you get back a value of 9. That's positive, which means that the slope is actually increasing there. If your derivative is positive, your function is increasing. It's going upward. So it goes up when it's less than 0. It flattens out at 0. Now what does it do at 1? Well, if you plug 1 into your derivative, 3 times 1 squared minus 6 times 1, you're going to get a negative 3. So that means your derivative is negative, your slope is negative, your graph is going to be going downward like that. And now finally you plug in 3 into your derivative. And let me see, you're going to have 27 take away 18. Well, by golly, look, that's another 9. So that's positive, so your function is increasing there. And now if you look at all those arrows that you just drew, you can pretty much see where the maximums are and where the minimums are, because your function is going to kind of go up, flatten out, and then go down, and then flatten out, and then go back up again. Your curve is going to follow those arrows. So in other words, everybody, if we can classify those points now as maxes or mins, right there, the 0, 0 is a max. That's a maximum, a relative maximum, not an absolute maximum. And then the other point right here, now that's when x was equal to 2, and we already calculated the y value as negative 4. That is a relative minimum, relative maximum and relative minimum. Now, of course, the other part to that question we haven't answered yet is for which values of x is the function increasing and for which values of x is the function decreasing. So I'll give myself a little bit of space here. I'll just erase that curve and I'll write the answer down in under. Now remember, you have to use your critical values, which are 0 and 2, as kind of like your endpoints. So here is the answer to the main question. Where is this graph increasing? Well, it's increasing here, and that's to the left of 0. So x is less than 0, but it's also increasing over here, you see, right? So that would be to the right of 2. So that would be x is greater than 2. That's when it's increasing. Now, where is the curve? Where is the curve decreasing? Well, it's actually decreasing in between those values. Right here, you see? There's where it's going down. In between the 0 and the 2. So I would write 0 is less than x, which is less than 2. And we have answered the question. That's where the graph is increasing. And that's where the graph is decreasing. So go back over your question now. Make sure you've answered every part. Find the values of x for which the function blah is increasing and those for which it is decreasing. That's these two right there. And then identify any maximum or minimum points. And that would be this answer right there. And notice that we used the table right there to answer both of those questions. Now, I don't think we have time to do example number 4 in this video, but if you look at it carefully, maybe we can get it started. And you might even want to try it on your own a little bit, perhaps. Now, I wonder, can I move that down? Yes, I think I can a little bit. This one says find all maximum and minimum points. So note that, that's important. So your answers are going to look like x comma y, and you have to identify them as maximums or minimums on the graph of the function y equals this thing. Now, I tell you what, that right there, that is a what we call a quartic polynomial equation. It's a degree 4. And when you find the derivative of a quartic polynomial equation, you're going to end up with a cubic polynomial equation. So you're going to end up with a cubic to solve. Hopefully it won't be too difficult. I think I'm going to leave this one for us to cover in class tomorrow, because that one's going to take us a little bit of time. It's not difficult. You can have a look at it yourselves right now if you want, or when you watch this video. You can have a look at it, but I'll go over it in class as well. What we do have time to do, though, is example number 5 on the bottom of that page. Now, this one is really straightforward. This one is really simple. You've got a really exotic looking curve there. And now, I don't know if you can determine what the degree of that equation would be, But one way to tell the degrees, if you look at the number of maximums or minimums, 1, 2, 3, 4, 5, this is a degree 6 equation. But you didn't need to know that. What it says to do is identify the local extrema. Now what that means is the local max or the local min, and then the absolute extrema. So the absolute maximums and the absolute minimums. Now you're going to assume that these two sides of your curve go up forever and ever and ever and ever and ever, and they go up to positive infinity. So let me see, what would you classify A as? What would you classify A as? Well, if you look at A, here's A, that point right there. Now it's definitely a minimum, but is it the absolute minimum? Is it as low as that curve goes? Is that the smallest y value on the whole curve? And it looks to me like it is. So that would be an absolute, minimum. Right there. Okay, now what about point B? What would you classify that as? Well, it's certainly not a minimum. It's a maximum, but it's only a maximum for like this small region of the curve. So there's lots of points on that curve that has a bigger y value, but for that little piece, that's kind of like a maximum. So this would what we would call a relative maximum. Now, of course, we identify relative maximums using the techniques we just did in example 2 and 3. What about C? Now that looks, there's C right there. Now that looks like a minimum as well, but it's not as low as A was. So it would be what we call a relative minimum. Right there. And then we got point D. Now, by golly, it looks like a maximum to me. It's right on the top of a piece of a curve. But it's not the highest point for the whole curve because these two sides here go up to infinity. So if anything, I would classify that as a relative maximum, not an absolute. In fact, this graph, this function, does not have an absolute maximum. And the last point there is E, right there. And by golly, that looks like a minimum as well. But there's points on the curve that are lower. So we would call this a relative minimum. Relative minimum right there. Okay, so that's the last example that's there. In class tomorrow, I'll go over example number 4 on page 10, and then I will get you to try the practice questions on page 11 afterwards. Okay, so I'll put that in your lesson plans. Now I'll post it all on the news feed on the D12. So until tomorrow's class, I will bid you a fond farewell, and I will see you soon. Okay, have a good evening.